How does inverse QFT work in quantum computing? Imagine you have a secret code in a language only quantum computers can understand. To decode it, you need a special tool called the inverse quantum Fourier transform. This process is like reversing a complex translation to get back to the original message. The inverse quantum Fourier transform is the opposite of the quantum Fourier transform. While the quantum Fourier transform changes a quantum state from the time domain to the frequency domain, the inverse does the reverse. It takes a quantum state that has been transformed and brings it back to its original form. The quantum Fourier transform works by applying a series of quantum gates to the qubits, which are the basic units of quantum information. These gates include Hadamard gates and controlled phase rotation gates. The Hadamard gates create superpositions, making the qubits hold multiple states at once. The controlled phase rotation gates add specific phase shifts between qubits, encoding frequency information. This process uses quantum properties like superposition and entanglement to do the transformation efficiently. It can handle many qubits at once, making it faster than classical Fourier transforms for certain tasks. To perform the inverse quantum Fourier transform, you run the same sequence of gates used in the quantum Fourier transform but in reverse order. Each gate is replaced with its inverse. For example, controlled rotation gates with phase shifts are replaced with their conjugate transpose, which negates the phase. The Hadamard gates are self-inverse, so they stay the same but are applied in reverse order. This reversal undoes the original transformation, turning the frequency domain state back into the original computational basis state. This process is essential in many quantum algorithms, such as Shor's algorithm for factoring large numbers and quantum phase estimation. After the quantum Fourier transform encodes information about periodicity or phase, the inverse helps extract that information. When the inverse is applied, measuring the qubits gives a classical result that reveals the hidden properties of the problem. It's like turning a coded message back into plain language so we can understand it. In simple terms, the inverse quantum Fourier transform works by reversing the sequence of quantum gates used in the quantum Fourier transform, with the phases negated. This operation transforms the quantum state from the frequency domain back into the original basis, making it possible to read out the information. It's a key step in many quantum algorithms that aim to solve problems faster than classical computers. Without the inverse QFT, many quantum algorithms wouldn't be able to produce the final results needed to solve complex problems efficiently.